Good morning, everyone. My name is David Dugagne. I'm with the ITASCA Consulting Group in Minneapolis, Minnesota. I'm here today also with Mark Christensen, who is the UDEC product manager and also the lead developer, and also with our software manager, Jim Hazard. So we're looking forward today to introducing you to some of the new features in UDEC 7. Just for your information, we are recording a webinar and it will be posted on our website in a day or so. If you have any questions, if we could just save questions to the end of the presentation, we will have some time to discuss any questions or comments that you might have. Everybody is muted, so with the webinar, if you do have a question, please just either use the chat dialog or raise your hand. So just a short background. UDEC stands for Universal Distinct Element Code. It's 2D software that was first released in 1985, about 33 years ago. Simulates the quasi-static or dynamic response to loading of media containing multiple intersecting joint structures. Large displacements along discontinuities and rotations of blocks can occur. The models may contain a mixture of rigid or deformable, i.e. zone blocks. So essentially a DEM, a continuum, or a combination of the two, where DAM is distinct element method. Version 7 represents a major transition from the GIC, which is the graphical interface for ITASCA codes that UDEC and FLAC shared, our 2D software. As we move to consolidating our software in the common framework, or GUI, our graphical user interface, which is used by our 3D programs for those who have used FLAC or 3DEC or PFC 3D. The comparison here on the right-hand side, we can see here is an example of a continuum or FLAC model in 2D, where we have zones and grid points, an interface where we can actually have sliding along a joint or discontinuity. We have UDEC and 3DEC sort of in the middle, essentially where we have a combination of continuum and distinct element methods, where we have a series of blocks which can be zoned, where we again have both contacts along the boundaries of the blocks and grid points within the block. And then you can compare that to PSC, which is our particle flow code, which is essentially a distinct element method and now block particle approach, where everything is based on contact interfaces. And essentially, your selection between the three mainly depends or largely depends on the increasing number of joints or fractures that you want to consider in your model. So just a quick overview of what we'd like to get through today. Essentially the overview of the new features that are available. We have essentially now two flavors of UDEC. We still have the more traditional GIC for those who are more comfortable with that interface. And then also we have the GUI, which again is the common framework, which is similar to what we have for our 3D codes. We have more online help. We have enhanced plotting in the GUI version of the software. We have updated command and fish syntax, as well as extended fish capabilities, an advanced built-in text editor in the GUI, new model construction tools, and new joint and discrete fracture network tools. We also have new analysis and data querying tools and other features. So when I speak of two flavors, essentially on the left-hand side, for those of you who have used UDEC in the past, you'll be more familiar with this interface, where we essentially have a structured tree setting, essentially our input in terms of commands and fish functions, our workflow at the top, and then our plot item in the main part of the model. In the common framework GUI, there's a variety of different layouts. In this layout, what we're seeing here, we'll look at this in more detail, but essentially several different types of panes, command line, console where we see output, multiple plot items or plots are available, a built-in text editor, and a file management system. When you're starting UDEC, after you've installed it, you will see in Windows ITASCA UDEC 7.0. And so UDEC 7 will launch the new Common Framework GUI, and UDEC 7 Geek will launch the more traditional view. So when we look on consider the Geek, essentially the Geek still retains a number of powerful interactive modeling tools for those who like to construct their models interactively. It maintains a unique project file, but the data and save files are actually common between the two platforms. In terms of the GUI, we have more powerful processing tools for pre and post processing. Again, the project file is unique, so you can't open a GUI project file in the Geek, but again, the common data files and data and save files are common. So primarily, I'm going to focus on the new GUI because that will be new to most of you who have used UDEC in the past. The look and feel of the Geek has essentially remained the same, although many of the new features, the enhanced fish and the new command syntax is incorporated into that format. So focusing on the GUI, and this is just for one particular layout, there are multiple options. We'll play around with that shortly. But again, what we're looking at here is essentially our main menu, contextual icons. So depending if you're focused on a plot or the text editor or the command line, these icons will respond. We essentially have a listing of all our data files and all our save states that are available in the model. You can simply click back and forth between different save states and so forth. The text editor, which we'll talk a little bit more about in a minute, essentially is built right into UDEC. It's designed for our commands, ITASCA commands, and for fish. So it makes it much easier. It's a really nice programming environment to be working with. Commands can still be issued manually, and we can also see responses to the commands and output from the model in the console. On the right-hand side here, this is essentially the control panel. In this case, the focus is on the plot, so the control panel is essentially showing what our plot items are and the attributes of the plot items. So we can add multiple plot items to a plot, and we can change the attributes accordingly. We can also see additional information, which is really nice, I think, because you can essentially inspect the program as you're moving the mouse cursor over the model. You will get feedback in terms of the location of the cursor and information about the objects that fall behind the cursor. We've put a lot of focus on our online help. We still have the manual PDFs. This is particularly important for the Geek. So for those of you who are used to our more traditional manuals, they're not available as a hard copy, but they are available as PDF. So if you're interested in the interactive controls that are available in the Geek for model construction, that is the main resource. If you're interested in the new command syntax plotting in the GUI, then the HTML-based system is ideal. And essentially that's just available through the main menu. We'll do a demonstration. You can still use the question mark in the command line in both the flavors of UDEC. Essentially, if you start a command, you put a question mark after it, hit enter, it'll give you a list of the keywords that are available. That's been available for quite some time, but it's being maintained. You can also use the cursor and the F1 key in the GUI to essentially get additional information and dynamically link to the HTML-based help. So essentially, if you put the cursor in the command line or in your data file, press F1, it will take you right to the page for that material, so you can see what the description is, what keywords are available, and so forth. The search box is available here in the top right-hand side, and then this is just essentially loaded in a web browser. I'm using Firefox in this example, and we can use the Control F, and we can use the find dialog to search within the document. So I think that'll be really helpful for people, especially if you're either learning UDEC for the first time, getting used to the new command syntax, or simply you are trying to refresh your memory. So we have a number of new enhanced plotting capabilities in UDEC. I think it's a little easier to work with. Essentially, when we want to add plot items to a plot, we create a plot, and this control panel on the far right-hand side, it's focused on what plot items we can add, and we can essentially just build our plot interactively, element by element. Once we add a plot item, such as a block, we can manipulate the range, and then we can change attributes. So essentially, we have labels and contours. So labels are things like ID, zone groups. Contours, of course, are things like displacements or stresses. And then there are additional controls to modify those. So just a couple examples of some plots that were done with UDEC 7 in the GUI. We can incorporate blocks, joints, contours, but also history and other chart information. We can embed charts within the models so that we can see what's going on as the model's running, or if you're saving files or essentially saving movies. It just is much cleaner and easier to work with. There's enhanced range logic for both plot items. So if you want to exclude or include certain elements of the plot, or this also works in terms of the model itself. So it's not just limited to the plot items. We can essentially go below our plot item. There's a range option. We add a range element. There's a whole list in terms of things that are visual, so positions, shapes, or property-based, like IDs, or even a fish function. So that's being widely expanded to be more consistent with our other software. We can export images and chart data. So here we've got a history, something that's going on, and we can simply right-click, export. Of course, we can export bitmaps and PDF files of the image, but we can also export a CSV file so that we can easily import that into a spreadsheet for additional analysis. Okay, so I'm just going to quickly go over to UDEC. So this is UDEC 7, this is the GUI. I've loaded in a model through a data file. So we have a data file here. The model's already being run, so we've got a couple of save states. I can look at the plot item. It's just a simple block with some topography, some jointing, a fault, and essentially what could be a tunnel excavated under it. So that's a simple model, but just to illustrate some key concepts. If I look at the stress, so this is the YY stress, so the vertical stress, and this is after the model's been fully solved. But if we look at an earlier state, we can simply click through. This was an initial save state prior to cycling, where we're just initiating some stresses based on the topography. So it's easy, very similar to what we had with the project tree, where we can flip back and forth and move between states. So when I click on the plot, we can see here on our control panel, we have a number of plot items. We can turn those on and off. They can actually be moved around. It doesn't really matter so much for the axis, but if you're plotting different plot items on top of each other, sometimes the order can make a difference. There are, it's possible to actually copy a plot item. So we can copy and paste it. Sometimes you might want to change some attributes. Perhaps you want to plot both the YY stress and the XX stress on the same diagram. So we plot the same plot item, change the attribute so that we have both YY stress and XX stress. And then we can offset the image so that we have two views of the model with different attributes. The attributes themselves, we can see here, we've got the ability to switch between contours and labels. If I flip to labels, right now that's a state label. This is an elastic model. So we can go and plot the model. See here in the legend, it's elastic. We can look at different properties. So in this case, the property is set to the let's see here, density. So we see this is the density of the model. And then we have different abilities to control things like zone outlines. So in that case, we can see the zoning and so forth. So I'm going to put that back to a contour. Here we're looking at displacement, magnitude. We could change that to Y or X orientation and so forth. So I think it's very easy to use, and I think you'll greatly appreciate both the quality of the plotting and the number of plot items that are available to you. So under file, of course, we've got new projects, save projects. We can add data files, which essentially just gives us a working space. You can see here we have a number of documents, plot items, the actual data file that made this model, and here I've started a new data file, which I've called test. We can change those around, rename them, different things like that. Under edit, it's essentially the same information that's available when we're in the text editor here with these contextual icons. So when we want to run a model, we can simply click here on the execute button, which is a screen button here. We can make new data files that are blank that we can complete, save them, load them, redo, undo. We can search through the file. We can do multiple commenting. So you can select, arrange, and then comment it all. So for those of you who've worked with our software commands, fish functions, it's really nice to be able to turn on and off for testing purposes or parametric work, different elements of the data file. Under layout, so the layout is essentially the structure that we have of the different panes that are available. So we can go to a horizontal project. Then, of course, you can resize all of these to work the way you want to. You can actually drag elements out and around, and then you could even save that layout. I tend to prefer the wide, but different people have different preferences. The documents are essentially just the tabs here, different elements that we have, and then we can turn it on and off different elements, different panes that are visible. Okay, so that's what I just wanted to talk about. With that, we'll be coming back to that illustration. So one major change is essentially, and we're doing this really with all our software, the 2D and the 3D, is essentially updating both our command syntax and fish. And really, the goal is to sort of unify everything and try to also ensure that the different commands aren't stepping on each other from the different products. And this is in part because, for example, we've released both TFC and FLAC 3D, where you can essentially have a FLAC 3D model and a TFC model in the same graphical user interface, interacting with each other, and you can manipulate that and work with it in the same space. So it's important that the commands be unique. We also hope that in doing the commands, that it will make it easier for people to learn the commands, because they'll be they're essentially very consistent, whereas traditionally or historically the commands were built up over time. Also, the hope is that it will be easier for people to remember. Now, one thing, when we look here, sorry, step back to the full screen. So here's an example. This is actually the help, the online help. It's in a web browser. There's all sorts of the table contents, index, and we've tried to make it as easy as possible because we do appreciate that it is a learning curve for everybody, and many people have pre-existing data files and functions. So we've tried to make it as easy as possible to illustrate how the old commands map to the new commands. Probably the first thing that you'll notice, in many cases, and this is unique to UDEC, essentially most things are initiated with the block command. And then it essentially, it's very, we think, logical. Block, create, polygon. And then you would have different keywords or labels after that. One thing you may notice is that some of them can be quite verbose, but I just wanted to point out here that while the formal command is block, create, polygon, and here we have a couple of points. As always, with commands, you can shorten those to just a few characters. So B, CRP, with the same points, does the same job. So it's once you get used to it, I think you'll come to appreciate it, and it's not as onerous, we think, as it may look. So here's an example. Here we have a UDEC file and a UDEC 7 after conversion. So instead of Y velocity, we have position dash Y. So there's some subtle differences, but I think it's fairly straightforward. What we've done in doing that, and we'll show you this shortly, essentially we have a converter tool that will automatically convert the old UDEC 6 commands into UDEC 7. And I find that it works really quite well, and it's a good way to sort of learn as you see your existing data files converted into the new syntax. Also saves a lot of time, so you don't have to reproduce everything. In terms of updated fish syntax, Again, in the online manual, we've got mapping from the old to the new. The main change here, which is what we're doing with all our software, is essentially moving to this sort of more consistent programming format where we have dots essentially separating the different elements of the fish function. Some new fish functions include data labels, scalars, vectors, and tensors. In the GUI, you can actually plot that. So if you wanted to plot scalar data of, for example, seismic events against your model, then that's something that's quite easy to do. We have email functions built in. So if you want to run your model and at the completion of the model, UDEC will send you an email letting you know that the job is done, and so forth. We can look at distances between points and segments and triangles, matrix math, so we can do transpose and inverse matrices, systems utilities for looking at directories and files, additional string options, and something which I find is quite nice is the inline fish, which is designated by these square brackets in the data file. So essentially, rather than writing a fish function to do a calculation of, in this case, area calculation, where we have the math.pi intrinsic, fish intrinsic, some variable squared, we can just simply do it in a single command line. You can also add inline fish within commands. So in this case, the command block zone generate edge. You could actually put in a calculation here rather than just a variable. So just quickly, this is just a video of a conversion. So what we're seeing here is essentially a UDEC 6 file. We've gone to edit, convert, and there are a couple of options, but when we convert it, essentially what it's done is it's produced a UDEC 7 command syntax version of the data file. I find that it works quite well. Sometimes for some of the more advanced constitutive models, because some of the properties aren't 100% clear, I think that's about the only time I've really seen it have issues. And when that happens, it actually gives you all the possible options of what could be converted. So you simply have to go in and take out the options that you're not interested in. When you do that, the original file isn't destroyed. It actually automatically creates a subfolder called pre-conversion, and your original UDEC 6 file is there in case something does go wrong or you want to revert back to your old file. So with the built-in text editor, we looked at that really briefly. Here we can see an example of a model that was run. I intentionally introduced a bug called bug into the command. UDEC did not like that, and so essentially it stopped on line 21. It highlights the line where the error is. It's also telling you here that there's an error on line 21 of the file that's being run. So in terms of debugging your models, your data files, I think you'll really come to appreciate that. We can see examples of inline fish where we have the square brackets. I'm defining a rounding length, some ratio, gravity, a radius. Then I'm calculating an area based on that radius, as per the previous example. So there's all sorts of these intrinsics, math.pi, cosine, sine, all sorts of math intrinsics that are available for you to use. Here we can see the inline fish is incorporated into this command. Essentially, it's a variable, but it can be changed here in one location rather than having to search through your file, find all of those variables, and update them manually. If you perhaps for organizing or some of the command lines can be quite long. You can essentially use these ellipses to indicate that we're going to continue on the next line, and you can repeat that over and over. In this case, we've got a create polygon with a lot of different vertices, and then those are designated with these little amper symbols. Of course, we have line numbering, which makes it much easier to reference where an error may have occurred. We can see here when we're in the data file, this control panel now becomes what we call a fish global symbol. So we can actually see the fish variables and what their values are. So if we were actually cycling this model and these values were being updated, we'd be able to see that in real time. Of course, you can see that there's all sorts of color coding to indicate numbers, text, and so forth. So it helps to make it seem much clearer. We briefly went over these different options in terms of creating new documents, running the model, searching through the data file, commenting and uncommenting multiple lines of code, and so forth. We can modify all the options of the text editor. So if you have font size preferences or font, if you prefer a different color scheme, those are all available to you. Okay, focusing on some new construction tools. Topographical stress command is a new in situ stress option. So essentially, we need to have gravity and material densities predefined before we issue the command. We can use our K0 to specify different ratios in terms of the different axes. So if stress is not uniform in the X or Z direction relative to Y, those can all be adjusted. So the advantage of this is you no longer have to do manual calculations to calculate what the stress should be and then initiate the in situ stress with those values. You don't require a fish function to loop through all the zones and determine sort of the lithostopic stress above, which is what this command is automatically doing, but we don't have to do that manually. And we don't require any cycling up front. So essentially, with this model, we simply issued one command, block in situ stress topography, K0X. So essentially, in the X direction, the stress is half of the vertical stress, and in the Z direction, it's a quarter. And you can see that here when we plot block XX, essentially, block YY stress is twice the XX stress. And that just happens pretty much instantaneously. It's now much easier to model cracks using DXFs. So here's an example of a DXF where we've got a slope, a valley, in this case, a number of tunnels. One thing I want to point out, it's still important because essentially we're generating cracks for those who are familiar with UDEC. So it's important that the cracks are through-going. So in this case, although these tunnels are in essentially solid rock, we essentially need a geometry or a construction line or crack to enable us to create a block relative to that crack. So we create a model new. That's some of the new command syntax. We still specify our round length and our edge length. Again, minimum edge length can essentially be M-E-L. So it's not necessarily more typing. We defined a polygon, which is essentially our bounding box, and which is the bounding box of this DXF. And then we're simply importing geometry from a DXF file, and then simply the command block cut geometry, and referencing back here to the name of that geometry item. we can see that we've created a number of blocks. So we could then simply delete this block above and continue on modeling. In this example, there's a video of it. We essentially add a whole bunch of jointing and Voronoi here into the slope, and essentially see the stability of the slope. So again, the construction joints are still required, and that it's really good for sort of the overall bulk geometry. You can certainly use it for jointing, but we have some more, I think, powerful tools that are available now for generating DFNs and jointing patterns rather than importing them through geometry. So we have here a 3D joint generator in UDEC. UDEC 6 used angle keywords to specify the orientation of joint sets. UDEC 7 allows essentially a specification in 3D space. So we're using origin, dip, and dip direction keywords to specify the joint orientation. And here we have a couple examples. We're looking at the origin, so essentially this plane here in 3DEC, and we're seeing that we're getting the same sort of jointing pattern. And the idea is that you could orient this plane in 3D space along any part of this model or rotate it essentially like a cup plane. We have asymmetric Voronoi generation. So generally the aspect ratio of the Voronoi generator, so you could think of perhaps this is going to be a rock cut, some kind of slot here of an intact sample, and these are essentially mineral grains. Or in the bonded block modeling world, we'll often try to represent intact rock by controlling the contact properties between these smaller blocks to allow essentially natural damage to occur as stresses are redistributed and materials yield. But in terms of the asymmetric aspect, we can now specify an aspect ratio. So here we see the grains get distorted. This is an example of Voronoi, but there's also a triangular trigon option. This is limited to the GEIC, but we've added a rock support database. So if you have bolt properties and you'd like to save them, if you've calibrated them, you want to save them into a database rather than having to re-enter this each time through commands. Just like we have a rock database, you now have access to a rock support database. In terms of fracture generation, essentially wanting to statistically represent DFN in a model, it's simple. Of course, it can always be complicated dealing with the statistics and how you want to represent what's actually in the ground. But in terms of the elements that you need for modeling these things, I think it's been greatly simplified, and this is consistent across our 3D codes as well. So first we have to create a fracture template, and essentially we're defining parameters such as size distribution, the position distribution, and the orientation distribution of the fractures. And then the second step is to actually generate the fractures from the template, and the fractures are generated until a specified stopping criteria is met. And these conditions include a fracture count. So we want 7 fractures or 10,000 fractures. They'll just keep populating the space. A target P10 measurement, which is essentially a measurement along a scan line. Target density, P21 in 2D or P32 in 3D. Target percolation volume. DFNs at some connectivity threshold. And also, you can always use a fish function to have complete manual control over how you want to generate the fractures and when it should stop populating it. And this figure here, which is from this 2015 paper by Rogers and Paul, kind of gives you an example for those that aren't as familiar with DFN statistics, where we have a borehole and we're looking at a P10 to a P10 of 4, 6. So essentially we're getting more and more fractures, more and more fragmentation or creation of blocks. It just kind of gives you an idea. Here's an equivalent 3D measurement of those values. So we have a lot of control over how we want to generate that. We can create multiple instances of the DFN so that you get a sense of sensitivity of your system. When you're generating the fractures, a couple other options, we've added a fracture combine, which is simply a way to simplify the fractures using a reference fracture based on smaller fractures relative to angle or distance. We'll show you an example. We can, the idea here is to prevent small angles between fractures, which can lead to very tight spaces, by eliminating these small spaces, we can improve the meshing. We can import fractures. There's several ITASCA formats that are available. You can also import and export a 3D fragment format. And you can also specify it using the built-in geometry logic that's now available in UDEC. So here's an example. Of course, it's not the whole model, but it's the statistical part reference to the DFN. So essentially, we're creating a fracture template specifying the size distribution. There's a default template. So if we don't specify the orientation distribution, it'll be uniformly distributed by default. So the command fracture template create, a name for the DFN, size, in this case it's power law, so it's an exponential of 3, and a size limit, so from 1 to 100 meters, if we're using meters, so essentially the fracture length. We can create one instance of the DFN within our model. In this case, we're going to use T10 measurement. So fracture generate template, referencing back to the template. DFN, a name for the DFN. In this case, we're going to generate it in this domain, this space, and the value of P10 is going to be 1.5. And we're going to be measuring that along a trace length. You can think of it as a borehole, where we actually have a measurement of our QD or fracture count, fracture frequency. So essentially the start and the end position of that scan line. We're merging fractures. So this is that simplification approach where we're combining fractures that have a relative angle of 30 degrees that are 1 unit apart and repeating that for an angle of 40. So this is the relative angle between those. And so that essentially you can think of as a cleaning tool. That doesn't necessarily change the statistics of it, but helps us prevent issues with bad meshing. So once it's statistically generated, we still have to actually invoke it, and we do that with command block cut DFN, and then the DFN reference. So we have a movie here where it's essentially the model's being run, and we're just going to go through and demonstrate how you would use the plotting tool to look at your results. So we're looking at displacement magnitudes, and it's important to appreciate that all of those joints are, in terms of the geometry, are fully through-going. You can see that essentially the joints extend either from across boundaries, or from boundaries to other joints, or between joints. But what we can do is essentially specify different properties in terms of cohesion or friction or others, where we can essentially designate that part of those through-going joints are actually intact material, and that's what we're doing here, where we can go through and essentially by saying that we only want to look at the jointing where cohesion is zero. So those are essentially where our actual joints are. The rest of the joint is treated essentially as a construction material and has high strength, like high cohesion, high friction angles, so that really displacements or openings or closings can only occur along the actual joint that we want to represent. We can include histories right in the same plot item. We could also have just created a separate plot item. So sometimes data comes in because it's represented relatively negative. So we can simply adjust that by flipping things around. So essentially that's a pseudo stress strain curve in terms of this example model. We can change the labels of the axes. Everything is completely customizable. So in the interest of time, I'm just going to skip ahead of the video. This is the actual running of the model in real time, so we can see the data as it's built up. This is the complete data file, which includes not just the CFN statistics, but all that's required in terms of the block, the geometry, boundary conditions, properties. In this case, it just gives you an idea. But with about 50 or 60 lines of code, we're able to generate a fairly sophisticated model. Okay. So this is the same model, but what I wanted to show you here is the data querying capabilities. So if we pick this cursor option at the top, with the question mark, you can see down here in the bottom right, as we move the cursor around over different elements of the model, we're getting information. In this case, we're over the geometry. Here, we're over blocks. If we actually click on the model, we can inspect a specific block and copy that data to the clipboard. We can do the same thing for zones. So essentially, it's a nice way to be able to inspect the model without, in the past, we probably would have had to have written a fish function, loop through all the zones, found a zone or grid point that was near some position that we were interested in, and now we can just do an actual manual inspection. So essentially, other elements that have been added, we've eliminated the save file incompatibility for future versions. So while we always essentially maintain that a data file could be used in new versions of the software, it was not guaranteed that a save file would work. So we reconfigured the way the save files are structured so that will be possible. We have additional extra variables for all objects. We've expanded the use of color for existing plots, expanded plotting of structural element results. There's the ability to track blocks, zones, and grid points as they're moving. There's an automatic brick generator to get sort of that repeating of the bricks. Failure stage for all contact models are now available. And automatic stress initiation, not just based on topography, but also based on a point, a stress measurement within the model. So that would be useful for, say, a deep underground mine or tunnel. In addition, there's also a factor of safety contour plotting that's available, which is one of our new analysis tools. So at this point, thank you very much for attending and for listening to our presentation. If you have any questions or comments,